This video is a demonstration of cross-queries over streams, or CRISIS. CRISIS has been developed by the Institute for Big Data Analytics at Dalhousie University in collaboration with Defence Research and Development Canada and Lockheed Martin. The goal of CRISIS is to support maritime-related decision-making, which is accomplished by processing real-time cross-dataset queries over various streaming, heterogeneous, and spatially distributed maritime sensors from multiple IoT infrastructures. Maritime sensors are relevant to defense and security and produce large volumes of spatially distributed data every day. When considering data from weather forecasting systems, such as those providing global-scale wind, wave height, wave period, or pressure data, the potential for understanding the cause and effect between environment and vessels increases, at the expense of managing the incoming data volume. When data from these different sensors are combined, there is a potential to predict and prevent negative defense, security, or environmental events. The ability to integrate such heterogeneous streams, to link them to previously stored information in databases or from web sources, to process streaming data, and to reduce the overload of information is essential in many of the maritime monitoring scenarios. The approach presented makes use of semantic web standards and technologies and aims to improve knowledge discovery in the maritime domain. In our demonstration, CRISIS uses three sources of streaming data. CRISIS uses data from the Automatic Information System, which is a common maritime data source that delivers tracking information about vessels worldwide. We cross AIS data with information provided by the International Maritime Organization. With IMO information, we can capture further details about the vessel, such as type and country. CRISIS also uses data from climate observations. Climate observation points represent weather data and related atmospheric information, such as temperature, precipitation, relative humidity, wind speed, and direction. They are available for numerous locations across Canada and are updated hourly. This data is provided by Environment Canada. Furthermore, we use ice observations from the Canadian Ice Service, which are represented as regional sea ice charts and used for maritime navigation, climate research, and input to the Global Digital Sea Ice Data Bank. The ice charts are created through the manual analysis of in-situ, satellite, and aerial reconnaissance data. The ice charts are updated daily and have information on ice concentration, stage of development, and ice form, following World Meteorological Organization terminology. Ice is represented by a dark red color over the water. The darker the color, the higher the concentration of ice in that particular region. When clicking on a vessel, a query is made to both the local database and the linked open data cloud. The LOD cloud is a set of connected and distributed data sources across the web that provide public access to structured and exchangeable data. LOD sources provide information such as geographical places and points of interest. Some of the most popular LOD sources include the DBpedia, GeoNames, and OpenStreetMap. For this work, data from DBpedia is used. DBpedia provides a complementary service to Wikipedia by making Wikipedia knowledge available in LOD form and allowing sophisticated queries against the Wikipedia information and datasets linked to it. All the data used in this demo is mapped and represented with standard vocabularies, thus resulting in a consistent terminology against many contexts. As well, ontologies are utilized to describe contextual relationships behind the defined vocabulary, thus allowing richer bilateral mappings. In particular, we use semantic sensor network ontology and particular domain ontologies. SSN was created by the W3C Semantic Sensor Network Incubator Group and initially designed for the ocean sensor observations domain. Once the data from the distributed and heterogeneous data sources are available in a homogeneous, contextualized, and ordered representation, the totality of the streams may be explored to generate new information. We run queries against the streaming and static data to identify abnormal events, since it involves association of information across multiple data sources. Our approach focuses on the semantic streaming models and engine to process data streams at scale. In this demonstration, we showcase 3 real use case scenarios for maritime-related decision-making. Scenario 1. Object movement associated with static geospatial areas. This scenario considers vessel movement and vessel speed limit regulations for defined geospatial areas. Different areas have different imposed speed restrictions. These restrictions imposed as a result of safety and environmental concerns. The framework should send warnings whenever incoming data indicate a vessel is not respecting the speed limit restrictions for the particular area of operation. In this example, if a ship is traveling over 20 knots for at least 10 minutes, an alarm will be triggered and the MMSI along with the ship's speed will be displayed. Scenario 2. Object movement associated with dynamic areas. This scenario considers vessel movement and temporally variable areas as represented by weather patterns. Marine forecasts provide temporally varying areas that are monitored by the RMSA system to identify those where weather conditions are deteriorating for a given period of time. Such conditions should be considered when planning vessel operation. Scenario 3. Object movement associated with quasi-static areas. This scenario considers vessel movement and quasi-static areas as represented by ice concentration. The Canadian Ice Service provides ice data on a weekly basis in the form of ice concentration, ice thickness, amount of open water, etc. Such conditions are important when related to attributes specific to the vessel, such as the vessel's ability to navigate through ice-infested water. The scenarios represent queries running indefinitely in the background and in real time. For demonstration purpose, we sped up time, where every 6 seconds represents an hour. Thank you very much for watching. If you have any questions, please refer to the paper Semantic Integration of Real-Time Heterogeneous Data Streams for Ocean-Related Decision-Making, published at the NATO Science and Technology Board IST 160 Specialist Meeting. This work is part of MEMIR, Research Relevant Information Management for Integrated Response project, which seeks to develop ideas and techniques for seamless integration of data streams of many IoT sensor infrastructures.